Okay, good morning. The first thing is you probably can see the slides. We have several announcements. The first announcement is assignment number 1. I think if you were not on Piazza, you really should register on Piazza because there are lots of discussions there already. Okay. Especially some student may encounter some understanding problem or some software problem. You should really go into Piazza to check the discussions and message, because the due date is September 15th, and we also said no late homework will be accepted. So you should really start early, work on it, and make sure you understand it. If you need help, you can go to CTA during their office hours. Okay? Especially for the last week on the September 15th, before that, TA will open additional office hours and will announce it in Piazza. But I strongly urge you to see the TA earlier, okay? You solve your problem. Of course, you have some problem, you can post it on Piazza, except you cannot post answers, but you can post how you solve some kind of problems in principle. Okay. Another thing is the wait list is cleared. Okay. We got a very long wait list, more than 80 people, close to 90 people on the waiting list. We took 50 additional students. Based on the student write down, based on the reason you write down, say why you must take this course this semester. Okay. If you do not have good argument on why you have to take it this semester, we actually recommend you to take it in the next semester, because we are going to offer it in the spring 2015 as well. Okay. So I think you already got email if you were accepted from Holly. I just checked with her. She says she already sent emails to everyone. Okay, to everyone who has got accepted. But accepted is a video-only session. That means you have lower priority to take seats here. Okay, only if you find there are some regular students who did not show up, you can take the seat. Otherwise, you have lower priority. Okay, but other things are treated just the same. That means you get same homework, same programming assignment, same exam. Because we have a bigger exam, we actually may arrange 2 to 3 classrooms. By the time of the midterm and final exam, we are going to announce if your last student ID is in what kind of range you are in different classrooms. Okay. So that's the arrangement. Another thing is about the project for the 4th credit. Okay, I already told you if you are registered as 4th credit, you do not want to do 4th credit work. You should do it early to change it from 4th to 3 credit course. A few students already did it. They sent me emails. I forward to the registration office in academic office desk. So if you decided you want to stay in the 4th, you have to attend the meeting. Okay, the meeting is 10 to 11 a.m. Friday, which is tomorrow. That's one time only meeting, because we are going to partition into different tasks. After that, there will be no concrete instructions. In that meeting, it will be an important meeting. The TAs, including some PhD student and postdoc, they are interested in working on this problem. They actually will give you the very concrete instructions. So make sure if you are on the 4th credit, you must attend the meeting. Otherwise, you lose a lot of information. You may not do reasonable work. Okay. So there are a few students, they really want to change from 3 to 4. That means they really are very eager to do this project. It is still possible. If you really want to contribute, you want to change from 3 to 4, you do the same thing is you send me emails. I can manage to discuss with the academic office to make the swap. But remember, you don't drop from 3, you add 4, because once you drop, you will not be able to add on, okay, because the class is full. Okay. Make sure we just do the swapping by emails. Okay. So that's about all the announcements. You also can download from the updated site if you are not quite sure. You see this slides is also there. Okay. Last time we said we are going to do a little lecture on the very last the distance measure, or we can say proximity measure. Actually, the KR divergence, we're going to give 2 or 3 slides. I actually changed a little. For that slides, I actually added 1 picture. So I changed it from 1 slide to 2 slides for the previous one. Okay. Because 1 picture usually worth 1,000 words. So it's better to have a picture. I actually download the Wikipedia KR divergence entry. That's a picture from Wikipedia, but it's a very nice picture, okay, to show you what is KR divergence. KR divergence actually is Kullback, Leibler. These are 2 mathematicians. They proposed this divergence in 1951. It's more than half a century ago. But it's very popularly used in statistical analysis, also in data mining. Okay, you probably later, if you read some research papers or read some textbooks, very likely you will encounter this measure. That's why we introduce you here. Okay. This measure basically is to measure the probability distribution. That means in the real case, you have a probability distribution. Some people try to approximate it. They draw another probability distribution. Sometimes the real probability distribution could be hidden. Okay, so you got 2 probability distributions. You want to compare what's the difference between the 2. Okay, suppose one is P, distribution PX. The other one is QX. Okay, you got 2 probability distribution. You want to see how different they are. Okay, that's the measure to measure the distribution between the 2. Okay. Remember, we measure 2 objects. You have multidimensional space. Usually it's numerical ones or categorical ones. That's fine. We also said for very long vectors, like high dimension data, you can use cosine similarity. Okay. Those are nice things because the distribution is very clear. Even cosine computation may be a little involved. Okay. But if I give you 2 probability distributions, how to compare them, that's the KR divergence. Okay. Why we do not call this one as a KR distance measure? Just because all the distance measures follow the metric measure, means A versus B, B versus A is equivalent. But here, P versus Q, Q versus P, you put in different order, you get different values. They are not metric. They're not symmetric. That's why they call this one as divergence, not distance. Okay. This one has been popularly used in information theory, like computing the relative entropy, computing information divergence, information gain, information for discrimination. It's very popularly used in statistics. How this one is defined? This one is defined as, suppose you get a Px is one distribution, Qx is another distribution. You want to find how far this Qx can approximate or can be closer to the original one, Px. That's a measure. Measure, they have 2 forms, one called discrete form, another called continuous form. It really depends on your distribution. Your probability distribution is in the discrete form or in the continuous form. Okay. For discrete form, you use this formula. That means you have a domain. For example, you may have k values. Okay. Then how do you do for each distribution? Okay. You take a px versus qx. Then you take a log. You sum. You time this px. You sum all things up. Okay. So you can think of px and qx distribution. You divide them. Actually, you know, take a log. You essentially take a log each one. You minus them. That's why you see their differences, right? You know the log. Once you have division, you take them back. It becomes log p minus log q, right? So that's why you take a log. You see the differences. That's why P and Q are not symmetric, because log P minus log Q is not equal to log Q minus log P, right? Okay. So that's clear, it's not symmetric. Okay. So this is discrete form, and once you try to do the continuous form, you take integral, right? Instead of sum, you take integral. That's you integral from minus infinity to plus infinity, because the distribution could be very, very wide, very long. That's why I get a minus infinity to plus infinity, right? So that's a discrete form and a continuous form. Okay. How do you explain this? Okay. How do you explain this conceptually, what it means? Okay. This K-R divergence essentially is try to see if you get a true distribution, Px. Of course, it could be hidden, you do not know. But you try to get another coding, like a Qx. Okay. Try to code this Qx to approximate Px. Because the Px you may not know exactly, but use Qx to approximate. Approximate means you may use different bits to code your Qx to approximate P. Okay. And that one essentially is saying once you code using Qx, you want to see what is the real difference between Qx and Px. So that's the reason you actually using this, we call representing Px based on some kind of approximation or some kind of model or theory. So that's why you get a Qx. So if you watch the picture here, you probably can see this Qx and Px actually is very close here, but Qx actually shifted. You can see Px, the distribution is here, Qx distribution is here. The axis actually shifted. That means that your approximation is not exactly the same. Your approximation actually shift a little. Then with this shift, if you take log, you try to see, you can see this, you take log on both, you times this Px. This Px is here, you time it, you actually get something like this. Then you finally, you take this area, to take the integral. Like here, you take the integral. That means this one just to vividly show, you know, there are some differences. The difference can be represented here. You can see this one, this Px actually is longer here. It's higher than, if you take this part, you look at it, this Px is higher. That's the area is higher, right? And that part of Px is lower. That's why it becomes negative. Okay. But that's not the whole story. If you want to calculate the K-R divergence, you have to take an integral on this in this area. You finally find it, right? So that's the general idea. Conceptually, you can think this way. Okay, that's the same thing. You can see if this Qx keeps shifting. Okay, this difference also keeps shifting. The integral parts also will become different, right? So that's conceptually you can understand this way. This is what Wikipedia actually gives you a very vivid picture. You get a feeling. Okay. So that's whole thing is explained why the first thing is why they are not distance measure. Because you take a log P minus log Q, which is not equal to minus, once it's minus, you cannot swap them, right? That's why it is not a metric measure. So you cannot call this one as a distance because all the distance is metric. So it's asymmetric, and it's not satisfying the triangular inequality. That's why it's not metric. Okay, that means this one, you reverse P and Q, they are not equivalent. So you cannot say P, Q, Q, P. That's not right. Okay. In application, usually you will say P represents true distribution or true observation, but Q actually represents the theory or model or approximation to the P. That means you try to guess what P is, you draw a Q. Okay. This one was discovered or defined or invented in 1950s, but it's a measure very, very popularly used. Actually, even this morning, I got a student, two previous CS 512 students who did a project, one extended in the summer. They worked out a very nice paper. Actually, what they want to compare is the time series. Time series is similar to the distribution. And what their major use is KR divergence. You can see they actually may or may not take my CS 412, but they found this one is extremely useful. They actually compare with the other method. They did not use this measure. They found their discovery is more precise. It's better. You can see it's very useful. Okay. So sometimes they also call this one as information gain, but of course information gain defined in many different ways. This is just one way they use KR divergence. Later, when you study decision tree, you may find the information gain could be defined in other ways as well. Okay. There's one subtle computation problem. Okay, I use this slides to address the computation problem, because in some cases, remember we say log Q log P, you're actually doing this, but there's a problem is sometimes you got suppose you got a P is 0. P is 0, you got a P log P. If P approximately 0, P log P is 0. This one may be able to solve. But what about a Q is 0? Q is 0, you got log 0, it doesn't make sense. You divide by this, divide by 0, you get infinity, right? So then you cannot say the KR divergence final is infinity. That almost cannot be comparable. Infinity compared to infinity doesn't make sense anymore, right? So why cause this problem? This problem in many cases caused by this reason. If you look at this example, you probably can see why this problem may, in real computation, it may arise. Okay. For example, you just look at the probability distribution. If it's discrete, okay, P and Q may have value at different parts. Okay, you can see this. Suppose you get a P is on value A, you get 3/5. Okay, on the B, you get 1/5, and C on the 1/5. But if you look at the Q, Q have A, B, D, but they don't have C. That means that the C value, it happens, Q does not have anything. You just think about it. If you have several distributions in your hidden, okay, P distribution, if I work out a Q, I try to approximate you. I do not know where you have the value, right? Sometimes I model A and B may be there, but I model D, but you don't have a D, but you have a C. I don't have a C, I have a D. We model somehow different. In that case, if I do not have C, that means the C's distribution, I have a 0. Okay. You do not have D, your D value is 0. No matter what, either P somewhere come at 0 or Q come at 0. That's a problem, because you can see anything divided by 0 become infinity. It doesn't make sense anymore. So how can we solve this problem? Because in real life, you do have this distribution, right? Because I do not know what you have. I try to simulate you. I put this particular D, I give a value, but C, I did not give a value. That's quite possible. Right? So in that case, how do you solve this problem? You still want to use this formula to compute. To solve this problem is you use a small constant. For example, 0.001. You use a small constant epsilon. Then you can compensate them. How do you compensate them? You can see how do you compensate them. You say original P, the D part is 0. Now I don't give it 0, I give it epsilon. Okay. Since I give this one epsilon, I still want the original distribution just the same, so everybody have to contribute something to my epsilon. How do you concentrate? You can contribute, you can see. You have A, B, C value. Okay. A, B, C value. I invented a D. I give the value 0. I have to borrow something from the others. How do you borrow it? You can see. This one said, you give me 1/3 of epsilon. You give me 1/3 of epsilon. You give me 1/3 of epsilon. You all give me 1/3. Get together, get a whole epsilon. So then the problem is solved, right? We still get the same summation. So that you can see, that's the way they solve the problem. Say P prime instead of computing using P. That means originally this P becomes P prime. Okay? And how do you get P prime? You invent something non-zero. And everybody has to contribute something to my epsilon. That's it. The same solution as Q. Q, you change Q to Q prime. Okay. And originally C has no value. I don't want to divide by 0. I give a epsilon. Then everybody has to contribute 1/3 of epsilon to me. That's it. Right? Is that clear? I'm not sure for your homework, because in your homework, you do require to compute KR divergence. If you check the homework, one of them is. Then you know if in case you got this problem, you should compute this way, then you will not get into division by 0 problem. Okay? So that's it. So once you have this, you can just put into the formula, they will give you the value, right? So that's a way to compute KR divergence in discrete form. Of course, in continuous form, you will not get this problem. Because everything, is just a function. Any question on this? Okay. Of course, you need some help. You go to Wiki. Okay. Of course, you can go to some statistic textbooks. But you don't have it. The best way is you go to Wiki. They give you lots of pointers. You can check this. We introduced this one because it's very popularly used. Likely in the future you will study data mining literature. You will see this very frequently. Yes. You say the B now is different, right? You can see once you add this epsilon there, there's nothing 0, so you don't have to worry about division by 0. So I mean, P is 0. P is 0. Actually, you can see this formula in principle it should be okay. Okay, but but this, remember, you are adding everything. If this part is 0, 1, you have many things adding together. Is 1 0 is still okay, right? So it's not a factual. But if you try to be symmetric, you put none of them is 0. You still add something. But if P log P, if P is 0, it's not a big problem. The problem actually is if Q is 0, that's a big disaster, right? Okay, so that's about the computing KR divergence. So we finish all kinds of measures. Remember the most popular used one, for example, numerical one, right? We use Euclidean distance, we use, like a Manhattan distance. But you should know there are, so many different kind of variables. It could be Boolean, like binary. It could be categorical with a nominal. Okay. Actually, nominal in many non-statistic books, they call it categorical data. If you look at my that my slides I actually changed a little because I want to make sure you know this is categorical. I actually put a categorical there instead of nominal, because some people not in statistics feel not very comfortable, just use nominal. I also say core nominally. So categorical and nominal, they are essentially the same, just different names. So that's the textbook. I put a few books there. You can read it if you want to get additional information about the data. Okay. This one, you know where it is? Probably very few people have been there. This one right in the middle of Australia is called Wave Rock. Okay. The rock actually is really pretty long, like a wave. You see this rock really from a wave. The people standing there is pretty small. Okay. You probably see this is they call wave rock, but it's not easy to access because you have to fly to very down part of Australia, not near Sydney, but near Perth. Okay. Perth is, the flight to MH370, they finally say going down to the west part of Australia or somewhere. That's Perth was the center to search. That's a very far away place. And then you have to drive a few hours to go down to this place. So we finished this chapter. Now we come down a newer chapter called data preprocessing. You know where this one is? This one actually is a real glacier. This is in Alaska. Okay. Alaska, very close to the ocean. Okay. They have you can see the glacier mare down or keep going down where. If anybody watched the film called Inconvenient Truth, it was like Alan Gore. Gore was a vice president. He actually wanted to show the picture about the global warming. He took their crew to take that picture right here. Okay. I took a trip down there. Okay. You see the glacier still falling down, but not as bigger scale as what Alan Gore actually showed. Actually, the tour guide said they saw that crew. The crew stayed there, wait for about a week, find a really big one falling down. They took the picture, then finally showing the TV. Okay, but the normal one, you still can see a lot of the things falling down, but not in that big scale. So once we said what we should study on the data, very important thing is data preprocessing. Okay. Data preprocessing means the data giving you not necessarily immediately for effective mining, because the data could be dirty, data could be from multiple sources, you need to integrate them, the data could be too much or too few. Okay. And so we need to do a lot of things on data before we can do mining. One thing is data cleaning. I mean, data need to be massaged and cleaned. Need to be integrated, need to be reduced, and need to be transformed. Okay. So we are going to all discussing those things before we really get into mining patterns or doing clustering, doing classification. Okay. The first thing is about the quality of data. The data actually you got from the web from many different sources, equipments, or instruments, right? So the data could be not accurate. Okay. Actually, people, for example, study weather. They found the weather, if you want to study the weather 100 years ago, 200 years ago, 500 years ago, you will find that the first thing is you study 100 years ago, the data actually missed quite a lot. There's something, most of the data is not accurate. Okay. But if you go down to 500 years ago, it's almost no record. Right? You only see some history that it's extreme weather, it's very hot, very cold, or something. You see some book, history book saying this, but you have no record. So the data accuracy, if you go back to the history, is very, very different. Okay. Another one is the completeness. Of course, some part of the data is very scattered. When I was in British Columbia, they actually showed the map. Said only the very south part, there were the total 5 million people in the whole British Columbia, which is much bigger than Germany. That time there was 2 Germany combined together, it still can only fit part of British Columbia. Okay. But the majority part was mountains. There were no people. You look at the weather station, the part on top of the mountain and the bottom of the mountain, the temperature is so different. The measure actually is very incomplete. Another one is consistency. Once you do merging the data, especially a company doing the merge, even you get into, for example, you stay in Holiday Inn. They have different states, different countries. They have different charging policy, different things. So there are many, many things that are not consistent. Timeliness, that means the data could be aged. Believability, that means the data whether it's trustable or not. Interpretability means the data whether you can really explain the data in an easier way. Right? So we will study the major problem. We partitioned this into 4 major things. One called cleaning, another called integration, the third one called reduction and then transformation. The final one we will study is dimensionality reduction. For data cleaning, if you really go to the web, you want to get everybody's record, want to clean it, you will find that there are several problems. One problem is incomplete. Incomplete means when people fill up the data, they actually leave something unfilled. For example, you go to Facebook, you look at the occupation. There are lots of data they do not write down their occupation, so it's missing. Another is noisy. Like you go to Facebook, they will say, what is your salary? You write down -10. Okay, that means wrong. Everybody knows. Or 0. And another thing could be inconsistency. For example, even people fill up the birthday and the age, you will find they are not consistent at all because you say age 42, the birthday is 2010. Right? So anybody knows it's wrong. And it could be that's the date he filled up his 42, right? So those kind of discrepancy happens especially on the internet. You'll find lots of them. Okay. And also they have this kind of inconsistencies. You look at the ranking, they say ABC, the other guy said 1, 2, 3. So there are lots of different things. You know they are similar, but human can read it, a machine cannot. Right? And another could be intentional. For example, if you look at the birthday, you will find that January 1st is so many. Just because people fill up the birthday, they don't want to fill up the real one, they just pick up a date. It happens that people January 1st is the most convenient way. So that's why you find there are lots of missing data, incomplete data, incorrect data. Right? So the problem becomes, we know there are lots of problems. The first thing is you may want to find what's the problem, what's the reason to get this problem. Okay. One reason could be, for example, you get an Internet of Things. You get lots of sensors to sense the data. One thing could be equipment malfunction. The equipment got a short of electricity, right? They get a malfunction. Another could be the original record is somewhere deleted, or the data actually entered wrong. Okay. And so there are so many different problems. We know that, but you do data cleaning, you have to write procedures facing the problem. For example, when you ask the user to fill up on the internet, like Facebook, those data, you know it's people not taking seriously. Some people intentionally try to hide something. But you got into equipment, it's a different story. Right? The equipment were not intentionally hiding anything. It's just some other problems. Okay. So, but how to handle missing data? If the data is missed, how do of course you can use human to fill it in, but even humans, it's hard to correct it. So there are several ways to do it automatically. Okay. One way to do it automatically, you just put an unknown. Okay, you say this one is not, I do not know. You just put unknown. But unknown, if you put too many unknowns, when you do classification, they were thinking unknown is a special class, right? So that may cause some problem. Another one people quite often to do is they fill up, they call attribute mean or class mean. Okay. What is the attribute mean? That means if you look at age, you do not know this person's age, you do not fill up. You just fill up an average age down there. You say probably that's not bad. But in many cases, it's not smart. The smart one they call this is class sample mean. What is class sample mean? For example, if you find this group of students are university students, instead of say the mean is 45, you put it in. You say, oh, this guy is student. The student mean probably is 23. You put in 23, 22. Maybe that's more accurate, right? So that means you look at the class, you put the class mean instead of all the mean. It's better. But actually, to fill up the missing data itself is a data mining process. Most people are using some kind of data mining to do it. How they do it is you try to inference. You base on multiple things. For example, if you know this student, you know he already took many courses, so likely this one could be a senior student or graduate student. You probably, based on this, you fill up the age a little bigger. If the students just got in, you just take 101 or something. You think likely is a freshman. You put it, like. So this actually is you use decision tree or Bayesian formula to compute it. You fill up the value, which is more accurate. So this missing data itself could be a classification process, right? Then about a noise data, there also have lots of different ways. It could be incorrect based on many problems. The most popular problem actually is data entry problem. That means you hire somebody to enter data, they can enter wrong one. So data entry problem. Of course, there are many other problems. And the noise data also could be caused by duplication record, incomplete or inconsistent ones. Right? To handle noise data, there are lots of different ways. One is called binning. Later, we are going to show you how to do binning. Okay, binning could be, take a bin median, bin the boundary, or bin mean, or something. Later, we are going to discuss binning. And another way is doing regression analysis. You fill up based on regression curves. You fill up the most possible value. And you also can do clustering. Clustering means you try to group data. You find this Y right in the middle of the cluster. You give a cluster mean or something there. And another called semi-supervised means you use some computer algorithm plus some human, intervene. You get a human computer work together. You may fill up some noise data. You can correct it. Okay. So the data cleaning itself is a big problem. Actually, I remember I got a PhD, they graduate, they usually do a little designing work, but I got some bachelor and master. After a few years, I met them. Quite a few people, I asked them what they are doing. They say they are doing ETL. What is ETL? You proceed, this is ETL. ETL means they got data, they do data extraction, data transformation, data loading. Essentially, they develop tools to do data cleaning, data integration. Why they have to develop tools? Just because you think about it, different kinds of events, different things, they are all caused either by human or equipment. Nothing is perfect. So you want to handle data, analyze data, even store data in the database. In many cases, you have to write programs to do those things, to do data cleaning, data transformation, data integration things. So that actually costs a lot of software and manpower. That means you go to any company, a lot of software people actually are doing this kind of work. That means that before they do data mining or even put in the database, they first have to do data cleaning. And data cleaning needs to write a lot of code because in different cases, you write different things. So that's why it took a lot of manpower. Okay. Some people got statistics, said they study data mining whole process. The data mining takes a lot of technology, but data cleaning takes a lot of money. They finally find that money-wise, data cleaning takes 70% of the whole budget. Data mining may only take 5 to 10% of the whole budget. You can see that means data cleaning needs a lot of work. Okay. And how to do this? You proceed. I wrote down a lot of things. The things is called using commercial tools, like doing data scrubbing, data auditing, and data extraction and cleaning. But remember, these commercial tools has to be very specialized. In many cases, you have to write by yourself. Okay. So then we were not talk more about data cleaning because you know you go to a different company, you write different software. Then we talk about data integration. Data integration actually comes in the real life is you got for example, the Oracle may acquire another company. Okay, you get a company acquisition. And then you have to merge this company data with your own company to form an integrated database. Those actually happens, company merge, acquisition, or you get data from different sources when you integrate them. And to integrate them, you got a data integration and a schema integration problem. Data integration, that means you got a multiple data sources when you integrate them together. Schema integration means even you got a tables. They are structured data. Actually, the schema defined differently. You have to integrate them. For example, you think this database called customer ID, the other one called customer number. Okay. Maybe they are the same thing. You finally have to see how to do transformation, right? And entity integration also has lots of problems. For example, you have different names, actually means the same person. Like Bill Clinton, William Clinton may be the same person, right? And same name may be different people. Actually, in the graduate level course, I do have one, paper. Say, in DBRP, they are like 30 Wei Wangs. This is exactly the same last name, first name, but they actually different people. They all author papers. Finally, you put all these papers together, you get a very long list. But many are completely different, right? You have to find an algorithm to split them automatically. Right? So that's a naming problem. Right? So another interesting thing is conflict resolution. That means you got things like you say this person, you got different ages, different birthdays. Maybe it's different people, maybe that's the same person, you get it wrong, right? So you get a conflict, you have to resolve it. That means which one is right? Whether you have to separate them into different records, different people, or something got wrong, you have to erase it. Okay. So this problem in data mining we call truth-finding problem. That means you get different things. Then you may finally find, something is not true. So you have to erase the wrong thing. So you have to get an algorithm to do it. We are not going to discuss this, but it is a good research topic, automatically finding truths. Right? And so doing this, you probably can see one is object identification. That means maybe that's the same attribute have different names. Maybe that's a different attribute have the same names. So how do you identify these the different things or same thing? This is object identification problem. Another one is derived data. Derived data in many cases may cause a lot of inconsistency. For example, you go to the web, you say Obama's age. Okay. You'll find Obama has many different ages. Some people say, oh, he's 46. Some people say 53. So what is real Obama's age? Actually, a lot of this age was derived data because Obama's birthday is a fixed day. Depends on which year, you know, the year he got elected, or the current year, or the year second time he got elected. That's all the different age. On the web, you show everything, okay? That's a problem of derived data, because the age is derived from the birthday. It depends on different year, you get different value. So that's actually derived data. Like you get a total salary or total income. There are lots of derived ones. There's taxable income or after-tax income or something. It depends on. That's why the people really like to see the real original data. Like when you fill up the form, they ask you to fill up a birthday instead of the age, because the age is changing, right? So there are lots of different ways to handle it and resolve it. That's why this like truth finding or fact finding becomes very interesting. Because you go to the web, there are lots of conflicting things, so you have to resolve it automatically. Okay. Now, a very important thing to recognize the redundancy is correlation analysis. For example, if you find that all the ages is correlated with birthday, then there's a potential you preserve only one, for example, age, and remove the birthday because they all can be derived. They are correlated. Right? The same thing, for example, if you look at the students' the grades and GPA, if all these different grades is related to GPA, probably finally you only preserve one, like GPA. You erase all those different grades because you know they are correlated. Then how can we do correlation analysis? That means how do you judge the two variables are correlated? I chop one, only preserve the other one, right? For categorical data, a very popular analysis for correlation is chi-square analysis. Okay. What is chi-square analysis? Okay. I better first show you the real example. Then you probably see what is chi-square analysis. Okay. Suppose I got a contingency table. Contingency table usually is to summarize a lot of different values and fill up a table like this. Okay. You first forget the things in the parentheses. Parentheses is the one I just derived. Okay. You just look at the original data. For example, you go to a school. You want to see whether like science fiction or playing chess is correlated. Correlated means either positive correlated, the people like science fiction, likely also like to play chess. Or negative correlated, that means people like science fiction, they don't like to play chess. Okay. So you want to judge this. You want to judge whether these two things are correlated. How do you judge it? You first get all the numbers based on statistics. That means if you ask everybody, you fill up this. Suppose you total, you ask 1,500 people, 1,500 students. Okay. Then you fill up the form. You find there are 250 people who play chess and like science fiction. But there are 200 people, they do not play chess, they like science fiction. But you'll find that there's 1,000 people. 1,000 people, they do not play chess, they do not like science fiction. You get all these numbers filled up. Okay. Now, I'm going to ask you whether play chess and like science fiction are positively correlated. Means if people play chess, likely they also like science fiction. Okay. Can you judge whether they are positively correlated or negative correlated? How do you judge this? To judge this, we actually have observed value. These are all observed value. Actually, remember, you actually just need 4 things to fill up the whole table. You can see you need this 4 number, fill up the table. And these number actually derived by like 250 plus 200, you get 450, right? Because this is all the people who like science fiction. These are all the people who do not like science fiction. These are all the people who play chess. These are all the people who do not play chess. These are all sum, total sum, right? That means all the number, you just need the 4, you get the whole thing. But what's the things in the parentheses? Parentheses actually derived, we call expected value. What is expected value? You probably can see why I fill up this one, call this is expected value. You can think this way, okay? Suppose I fill up this one as 90. You say, how do you get 90? Get 90, you think about this. There are total 300 people who play chess. If play chess and like science fiction, they have nothing to do with each other. That means you can just, based on the proportion, you can guess it. Then what I will guess is this number should be 90. Why it should be 90? You think about this, okay? You think about it, like science fiction, there are 300 people, right? 300 people, but you get a 450 like science fiction, and out of total 1,500 people. So that means the proportion of people like science fiction versus all. And here, if they have nothing to do with playing chess, you got the same proportion. That means 90 versus 300, and 400 versus 1,500 should be identical, right? Because you think about this. These are the people who like science fiction, not like science fiction, right? These are the people among the whole population. If playing chess has nothing to do with like science fiction, then the proportion 90 versus 300 should be the same as 450 versus 300. Is that true? You understand this, right? That's it. That's why this 90 is expected. That means I assume playing chess have nothing to do with like science fiction or not. So I should get 90. So you probably can see you get an observed value is 250. Expected value is 90. That means if they have nothing to do with each other, this slot should be 90. However, now you get 250. It's far more than expected. So likely, you can guess, likely this is positive correlation. That means playing chess, likely they also like science fiction. Otherwise, they should have 90 people. How they get 250 people, right? You can see the reasoning. That reasoning is reflected in this chi-square analysis. And how do you do this? You probably can see I add this up. The real formula is here. Okay. The real formula is this E means expected. Okay. This O means observed. Okay. You observe 250, you expect only 90. So for this particular slot, you get 250 minus 90. You square them, divide by this 90. You got one value, this slot value. Okay, so you probably can see this first slot, the left upper angle, this first slot, you get 250 minus 90 divided by, you take a square divided by 90. Why you take square? Because you don't want the positive and negative cancel each other. Okay, everybody's square. Then you divide by 90. This is the first slot. Okay. So then you can see, you can get a second slot like this one. It's the same thing. You take a observed one minus expected one. You take square, you divide by the expected one. Right? The same thing, you calculate the third slot, the fourth slot. All the four slots you calculate. What's the result? The result, you add all them up, you get a pretty big value. This pretty big value, actually you can do further analysis. Usually, if you can think about this, if they have nothing to do with each other, or everything is in the expected one. That means if everything, you expect 90, they really show 90. You expect 210, they really show 210. Then the final everything should be 0. So if everything is 0 or something close to 0, then the chi-square is close to 0, that means actually playing chess and like science fiction have nothing to do with each other. They are independent. They're not correlated. Okay? But if the value, you add them up, they are all very different. Okay? You get a pretty big value. That implies they really, really matter. Like science fiction and play chess, they really matter each other. They really strongly correlate. Right? People can see. That's the reasoning. You judge correlation, you find a chi-square has a pretty big value, you know they are somehow correlated. But because you take a square, you actually do not know even positive correlated and negative correlated. Because no matter you minus small minus big or big minus small, once you square them, they all become big. Right? They all become positive. Right? That means you get a pretty big value, you know they are correlated. Whether they are positive correlated, negative correlated, this formula itself does not say. But you can easily judge it because this one is pretty positive. Because this one minus this, you get a pretty big positive number. So then you know they are pretty positive, right? So that's the general idea or general philosophy. Okay. Rigorously say, if you really want to do this, you first compute chi-square. Then you do the null hypothesis testing to calculate the p-value. I'm not going to give you the details, but if you study statistics, you should know. You assume your null hypothesis means they have nothing to do with each other. Okay. Then you got a pretty big value. That means the chance to get a null is very small. Like this value is very small. That means they are correlated. The positive and negative, you based on this, you can judge they are positive correlated. Right? Once you know they are positive correlated, actually you can cancel some attributes, you preserve some valuable ones. Like age, is positive correlated with birthday or birth year. You preserve birth year just to throw away the age. You still can do the right analysis, right? The same thing as your salary or some kind of a tax or something. They are positive correlated. You can throw away one, you can preserve the other. So that's a data analysis. For chi-square analysis, those kind of a study, you can easily see. You can get the very popular one is chi-square. Okay. So this you can see is you first do null hypothesis. Say these two distributions have nothing to do with each other. They're independent. Then you calculate the chi-square. Okay. Then you can get a correlation. But a very important thing I should say, correlation does not mean causality. Okay. Of course, you can say birth year and correlation, maybe they are really causality because you were born there. Every year you grow older. So they are really causality. What about this? What about you see number of hospitals and the number of crimes in a city? They are positive correlated. They are correlated. They are positive correlated. If you get more hospital, you get more car theft or more vandalism. So is a hospital cause vandalism or vandalism cause hospital? Because they have nothing to do with each other. They were all caused by the population. You get more people, you get more hospital, then you get more car theft. Right? So the real reason is the population is not the hospital caused the theft or the theft caused hospital. Right? That means correlation does not mean causality. Okay? To really get causality is hard. You really say this one causes is hard. But the correlation analysis is somewhat easy. You just based on those numbers, you can judge whether they are correlated or not. Right? So that's a very important thing. You can easily say, I dare to do correlation analysis, but for causality analysis, you want to be careful to put the conclusion there, right? Because it's not easy. Now we get into numerical data. Last time we just say the playing chess and reading science fiction. Okay, those are the behaviors. This is a category data. But what about you get all the numbers? You get numbers, you want to study correlation. You first have to understand the variance and covariance. What is variance? I think we already got a little discussion on the variance. Variance essentially, we use those standard deviation. I think last time we already said how do you get this? Okay. To get this for the discrete data is every time you take suppose you get 100 different points, numerical data, like a salary. You get salary, you can sort them or something. You find mean, find the center point, the average. You get everybody's salary minus this mean. You take a square, okay? So this one essentially finally you get is the variance, okay? For example, you can assume this. If the company, everybody got the same salary, then you minus this mean, you get a variance is 0 because everybody got an identical salary. Of course, it's not real. Okay. What about the salary get very different? Like a Bill Gates get 10 million, you got only like 10,000, right? You get this, you get a very big spread. Then you get a mean, you minus them, you square them, you add them together, you get a very big variance, right? So that's why the variance, or you can use standard deviation, you can easily see how the data is spreading. This is for one variable, like salary. It's only one, right? So that means you can get a variance, you can get a standard deviation. I think everybody knows this. This is like a common sense already. Okay, and also you can calculate the more efficient way. We said you calculate this way is more expensive. You calculate the other way like this is, from the computer-wise, this is much easier to calculate because incrementally you can do incremental algorithm easily, right? This is about a population mean, population variance, and the sample variance. The sample variance essentially is you only have limited samples. You can do 1 to n, you can get this variance. Now, I introduce, I do not know whether you know it, but I think probably a lot of people already know it. How many people knows covariance? Yeah, we got probably over half. That's good. The covariance means you get two variables, two numerical values, right? Then you want to see their covariance. The covariance actually defined essentially is, you can see originally you have only one, right? One mu. Now you have two variables. You have mu1, mu2. You have two, mean value. Then you get every variable, you minus them. This time you don't do square. You time them together. Okay. You time them together, you get covariance. Okay. This is the original definition. You also can do transform into something easier to compute. Is this one. You can transform this. You can easily prove they are identical, right? The same as a single one. So once you get this covariance, you also can calculate remember this one, the definition is you don't take the square root. The reason is actually it could be even negative, right? You probably can think about this. You time yourself is always positive, right? You get a square. But you time with the others, it could be positive 1, could be negative 1, could be positive pretty big, negative pretty big, right? So that's the reason you get this. The calculation is only when you get the same variable, you actually get this one square. That means you will think the covariance and the variance, the original variance, just a special case of this covariance. When these two are identical, you get a variance. Otherwise, everything's covariance. Right? Then for the covariance, if the covariance is positive, and you can say this is positive covariance. Actually, this is immediately you will think about this is somehow like a positive correlated these two variables, right? The negative covariance in this interesting thing is if they are independent or purely independent, okay, strictly independent, the covariance actually is 0. However, not all these are 0, they are independent. That means the reverse is not very true. And there are data, actually, they may have multivariate normal distribution, and they may have covariance 0 as well, but they are not independent. That one later, you can check the statistical big examples. Right? But now we will see how to calculate this covariance, and later we'll see how to get a coefficient, a correlation coefficient. So you probably see, suppose you got two stocks. Okay, maybe one is Microsoft, one is Google. Okay, you want to see whether they are positive correlated or negative correlated. Okay, what do you got? Suppose you got the stock value like this. This one is 1, 2, 5 means one is, say, Microsoft, one is Google. Okay, so they, in the 5 days, they give you this 5 values. So you want to see whether these two stocks are positive correlated, negative correlated, or nothing to do with each other, right? You want to calculate this. And how do you calculate this? You just use the covariance formula like this. Of course, this calculation is a little involved, but you can calculate using a little simpler one, right? That means you first find everyone's mean, or say expectation, right? And then you use this formula. You can see this formula is you time everything together, divided by, because you need to divide by number of elements, number of pairs. Then you minus this two mean, or you can say two expectation time together. Right? So that's the way you calculate the covariance. Right? I assume it's pretty easy. If I give you a formula, you probably can do it very quickly. Okay? Now we get into correlation coefficient. Correlation actually is the standard covariance. So-called standard covariance is you get covariance here, you want to standardize them, normalize them. How do you normalize them? You just take each one, just say they vary on themselves, right? You get a variable 1, you say variable 1's variance, variable 2's variance, then you use their covariance divide by their product. That's it. You got this correlation coefficient. Okay. This correlation coefficient actually was pretty famous one. They call this one the Pearson correlation coefficient, because this was Pearson first to work out this formula, right? And for this one, if you got a sample, this is the population one, you get sample one, you just take the sample, you calculate it in the same way. You get this correlation coefficient. Okay. And what do you really mean this become an important factor? Because you can easily judge whether these two variables are positive correlated, negative correlated, or somewhat independent. Okay. So the rule is very simple. You already know this covariance, like we said in Microsoft and Google stocks, right? They go up together, or they one go up, one go down. So you easily can see whether they are positive, negative correlated. So now you can see if this correlation coefficient, okay, is greater than 0, they are positive correlated. If negative than 0, they are negative correlated. If they are 0 or almost 0, they are independent. So that means you calculate their covariance correlation coefficient. You can easily get their positive and negative correlated. Probably the best way to show you is, you show you in a we call scatter plot or something. If you randomly put the values, you calculate the correlation, you probably can see. -1 is strictly negative correlated. +1 is strictly positive correlated. Then anything closer to 0, you can see this is closer to 0. If it's 0, they really have nothing to do with each other. You can see it's pretty random, right? And anything going closer to -1, you get this. You go to closer to +1, you see they are more and more line up in this way, right? So you go up, I go up as well, right? Actually, this correlation coefficient, you can see based on this, you know the range. The range is -1 to +1. Okay. Because it's normalized, it's standard. If you really look at the covariance, they can go very big. They can go to +infinity or -infinity. They really have no limitation, right? So that's the covariance and correlation. Quite often in the exam, I ask people about the range. You should know what exactly I'm asking. You know, is it +1, -1, +infinity, -infinity? It depends on what you are saying, right? Then finally, I should introduce in data mining literature, in many cases, you are not only compute one, you compute many things together. That means you are computing x1, x2. Actually, you got suppose the variable actually has different dimensions. Okay, then your computation is not computing one, you're computing many. In many cases, when you compute many, you will get a matrix. Okay. For example, suppose you have x1, x2, you want to compute the different thing. You say this sigma 1 is itself. Okay. Then you have 1, 2, 2, 1. If this, if the variable is symmetric, you may get a symmetric 1. But you can see this is their covariance 2, 1 versus 1, 2, this covariance. This is their own variance by itself. So if you have, all the different dimensions, for example, you have n times d dimensions. Then you look at this, you may get, total n times d. This is a variance. This is a covariance. You finally get a covariance matrix. Okay. In many data analysis, you get a multiple variables. You want to see all their different variants, whether they are correlated or not. You need to compute a covariance matrix. Covariance matrix is just a little more generalization than the variance covariance we just discussed. Now this is the one we finished this lecture. So remember, this lecture is reasonably long. I still will suggest you download slides, you read it beforehand, because sometimes we get more and more analytical. Okay, thank you.